Good morning, everyone. So this particular video is the last one in the group of three videos recorded for a lecture scheduled for Friday. Section, the end of section 8.1, most of it is done in class. All section 8.3, this video recordings links are posted in Brightspace and they were available on Thursday evening for everyone. And then this is the last one that is very important, includes information about section 9.3, partial decomposition, partial fractions, an overall explanation of the reason why we do partial decomposition, partial fractions, and then two specific examples, one of them directly from the final exam review. As I mentioned in the final day of class, we're going to continue um, including the lecture notes in 9.3 to go over not only new topics, but questions of the final exam study guide. Final exam is scheduled for next Friday. It is scheduled during the class time, estimated to start at 10:30 and at 12:30 p.m. So we're going to spend time today during this recording and Monday and Wednesday, not only going over new topics, but going over questions of the final exam study guide. I'm starting off with two short demo presentations, going over some directions of the project, final project, and then showing you examples on a very short example on how to use some important tools to implement into your project in order to complete them successfully. So let me start off with that. So I'm going to go ahead and then share screen. So what I'm sharing right now is the site of Met 165. And then there is this very important announcement on the final project. So I'm going to update this announcement as I'm going to do with some others because these are important reminders. So today is March 9th. I'm going to place this on the 9th and then update it. So now this becomes the first one that you see there. In addition, I will continue to update some other announcements as well. Now, what is important for this announcement? Project is due Friday, which is March 14th. It's coming up Friday. You're not submitting the project electronically under any circumstances, since this is scheduled since the beginning of the semester, and the project were handed out and available to everyone almost 3 weeks ago. There is no way that you can come up with a reason not to turn in the project in class on Friday. So do not, that's why you see this bolded, do not submit the project electronically. A hard copy of the project must be turned in class. And you see some directions. Now, I received an email from one of you saying, what is this hard copy? Hard copy means a paper that you received in class almost 2 weeks, 3 weeks ago after you finished exam one. There's two copies of the projects, hard copy paper, that are handed out in class. One project version A, one project version B. I'm not printing out new copies. If for any reason you cannot find them, then you must go to content and then look at this module project right there. And then you see project version A, Word document, project version B, PDF document. Now, what I'm referring to is a hard copy. So if I'm going to download this copy or click on so you click on this little arrow sign, download it, save it in your computer and print it out. Now, the hard copy that I gave you, the paper-based, it's going to be the cover page. That's the cover page. Why is this a cover page? Because it has all the information that is needed. Section number, the name of the course, CRA number. These are all included in this cover page. So all this information with the objectives that I encourage you to read them very carefully. Everything that you see in there it is going to serve as the cover page of the project. Now, of course, you're going to do additional work to solve and then complete your project. All the other additional copies must be attached on the back. And then it is your responsibility to staple them together. Do not use a paper clip, staple them together, and then turn them in. The only thing that you do is on front page of this copy, you write down your full name, first and last name. The rest of the information is already completed. Now, there are two versions under the module project in Brightspace. Some of you want to type in the work that they do to complete the project. You can do that after you click on the arrow sign, download the Word document version, and you should be able to type in. If you are planning to do handwritten work, and this is what the directions are saying. So if I go to the announcement, one of the directions is saying handwritten work is accepted. So that means you can use handwritten work. Make sure to use a pencil that is dark enough for me to see it. And then staple all copies together using the one that I just showed you as the cover page. That's what I meant with the cover page of the project. And this was explained in class many times. So you cannot just turn in separate copies and then expecting me to staple them together. Or you cannot turn in something without the cover page. Once again, what's the cover page? Where do you find it? If you cannot find it, the copy that I gave you, the project copy, you go to content, you go to the module project right there. Depending on the version, let's say you selected version A, you're going to click on the arrow sign, download it, and print it out. That's what I meant by the cover page. This one has all the title, the information that is required. And then everything else that you do to solve the project, you staple them together on the back. That is part of the rules. Now, let's focus on, let's say you selected project A. Part of the project A is to select two countries. So that's going to bring me to the announcement again. So I'm going to go back to the announcement and then select the announcement that refers to this component of the project that we call it project presentation. This is going to take place the last 20 minutes of class on Wednesday, last 15 minutes, at most 20. That's what the announcement is saying. Use a short index, a small index card. You can use a big one, but has to be an index card, not just a formal presentation. There are three things that you're including in there. Any of those versions of the projects is asking you to select two countries of your interest. You're going to say the reason why you're selecting them, and then one interesting fact for each country that you selected. That's another announcement that relates to the project. So I'm going to place this under the updated version. And then what you do with the selection. So once you select them, you're going to do that short presentation, very formal. You're sitting where you are, and then you're reading through the index card, simply sharing with everyone your selections. You don't have to explain for which project you selected. You have to say, these are the two countries that I selected. A very simple reason. You may end up saying no reason at all. Or if you have a reason, just share it with us. And then one interesting fact for each of the countries that you selected. This cannot take more than 30 seconds to allow everyone to complete within a period of 15 minutes on Wednesday to fully complete the oral presentation. And that's going to add an additional point to your project. Now, let's say you selected project A. What is the main idea behind it? If I go to the content, project A, simply by reading at that version A, I understand that this is about the global factors that impacting the world population, growth population. So this entire project, for everyone that is confused, it's focused on the growth model. Where do you find the growth model? That is chapter 4 of our textbook, specifically section 4.2, 4.6. This is where the applications of the exponential functions are. So this is about an exponential model. There are two major exponential models that I explained in class. Both of them are given as y equals y0. That's the initial times e to the power RT, where R stands for the growth, or KT, where K stands for the growth model, for the growth constant. So specifically, if I go to content and then click on the course materials, you must have this in your lecture notes of section 4.2. But if you have a very hard time finding them, this is where section 4.2 is, right there. That's the PowerPoint. So if I click on the PowerPoint, that's going to show up. And then as I explained, this PowerPoint has different slides. So if I go through the slides of the PowerPoint, you are going to see models that are specifically designed for exponential growth, exponential decay. These are interest models, again, that are based on the population growth, population decay. So you look at examples that are provided in there just to have an idea how this is going to work. That's one reference. And the other reference, if I go to section 4.6, under the course materials again, 4.6, I click on this model. And this is where you see more specifically information about population growth models. So create models of exponential growth, exponential decay. And as you notice, the two models, these are the two models. You're referring to the exponential population growth, that's your model. So y equals y0, e to the power kt, where k is the constant, that, or the rate of change. So the constant is positive to reflect growth, is negative to reflect decay. That's what this model is all about. In your case, it's a population model, so that's going to be your model. This is your reference to work with the population growth of the two countries. Is this enough? No, it's not. You are going to determine this K using Desmos. So what I'm going to do now, I'm going to add a tab, and then I'm going to type in Desmos. And then I'm going to go to the option Desmos Graphing Calculator. And then I click on this plus sign, and then go to the table. Now, your table is about two variables, x1 and y1. Remember, the model uses y and uses x. Desmos uses x1 and y1. So your y has to be replaced by y1 to connect with the table, and then x has to be replaced with x1. And by the way, once you create the graph, you can work with the graph, and then you can simply copy and paste, or you can take a screenshot of this and then simply click on snipping and then just cut it and then save it and then print it out and then attach it to your paper. This can be done as well. Or simple copy and paste into Word document, but can work in both directions. Now, what you do, if you read the projects very carefully, it is asking you to provide and then get information from the links that are provided for the population size on the countries that you selected. And there's a group of links that I added into the project. If you have a very hard time working with them, there's another link that is giving you some reference to connect with our library resources. And the library has a research assistant program that gives you the opportunity to schedule an appointment one-to-one virtually or in person with one of the assistants at the library, and just explain to them that's what you're looking for. You need some data for the population growth in these two specific countries for this number of years, and they're going to give you additional links in addition to the ones that I'm providing in the project, and then direct you precisely where to go to find that information. Now, you're measuring this by decade. The word decade means every 10 years. And there has to be a starting point. So if I say for the past 6 decades, now this is year 2025, so you have to go back by decades, 60 years, starting 2025. So if I go back by decades, then 2020, then 2010, then 2000, then 1990, 9080, 9070, 9060. So 9060 for you is going to be the year zero. So you're not going to end. This is measured. There's two variables, the population size versus the decades, the number of years. So your variable X is the decades, and then your variable Y, X1, and your variable Y1 is going to be the size of the population. Now, when it comes to what you're entering to generate the graph, you're not going to enter the actual year 1960. You're going to call this year zero because this is the year that you start measuring the population size. So year zero, and then I'm going to move to year 10. So that means decade, 1 decade. I'm sorry, I started accidentally with year 1. So year 0, year 10. And then if I do that, the next one is going to become 20. So if I go by 10, it's going to show me year 20 automatically. So let me back up. So I'm going to click on the table and then start with year 0. And the next one, I'm going to type in 10. And then depending on how many decades you're counting from the year 1960 or 1950, look at the direction of the project. I'm not going to provide every single detail. It's going to automatically generate that. So I'm going to go all these decades, right? And these are my values of X1. Now, what's going to happen to Y1? You're not going to enter the entire population. Let's say I selected a country that has a population in millions. You're not going to enter millions because that's going to complicate the graph. But what you do is you omit the word million. Let's say the population is 4 million. So you're only entering 4. In the year 0, which is 1950, the population is 4 million. You're just entering 4. You're not making up numbers. After the country is selected, you have to search and find the size of the population during the year 1950. And then you're going 1 decade to 1960, and then find the number of the same country of the size of the population in the year 60. Now, could be a scenario that the population goes by 5,623,000. So if the size of the population is closer to 6 million than the 5, you're going to enter 6. If it is closer to 5 million, omitting the other numbers, then you're going to enter 5. If it is right in the middle, then you can enter 5.5. That's still okay. Or you can enter 5.4. But the idea is you're not entering large numbers to make the graph less complicated. And you're not entering every single element in that size of the population. So you're looking for a whole number or maybe possibly with 1 decimal place. So that's going to allow you to create a better graph. And let's say the size of the population after 10 other years became 5.5 and then became 6, became 6.2. That's acceptable as well. But you can go by 6 million as well. And then 6.8, I'm just throwing some numbers, and then became 7 million. And now you notice that some individual points are showing up. So I have to zoom out for you to see those individual points. See, there's some individual points showing up in there, but they're just individual points. They're not connected. And that's not what you're looking for. So what are you going to do to connect? Then this is where the model is required. So you're going to click on the next tab. You're going to go back to this plus sign, and then now you need the function expression. So what is your function expression? Remember, y is the variable function. X is the independent variable. Y depends on X. But this is not just Y, it's Y1. And that's what you're entering. You're going to click on this arrow sign, and you're going to put Y1. Once you do Y1, that tells you exactly what the numbers are for Y1. Since the numbers are approximated, you're going to click not on the equal sign because you're not entering population size exactly as it is. You're doing some approximation. So therefore, you're going to click on ABC, and then you're going to use this. We call this a tilde sign or the approximation sign. That's an indication that you're approximating. And now you need the model. Your model is variable y0, which is the initial size of the population. Don't call it y0 because if you do, that's going to mess up your table. Call it A to make it easier. This is the initial. And then you're going to multiply this by E to the power. This is where you get the power. To the power. What is the power? Is K. And then, of course, your variable is x1 because y is related to x1. So x with the little one. And then once you do this, if you notice now, once I do this, let me move this keyboard, and then I can, so now you see a graph, which is more likely an exponential graph. See, this particular graph allows you to make prediction. How are you going to make prediction? So let's say these 6 decades are getting me close to 2020. By the way, you have to count. So you can make prediction to find out what the population is going to be in the next decade, which is 2030. So all you have to do is 670, 80. So what's the size of the population? Let me zoom in a little bit. So 70 is between 50 and 100. So then I have to search to find this 70. So where is my 70? And what the size is going to be? At this point, I don't know. So I'm gonna, this is 69, you see, so I'm gonna click on the graph and then move this to 70. You notice, once I move it into 70, it's predicting the size of the population to be 7.7, so roughly 7.8 million, right? I can do this for 80. So if notice if I move this along the curve, now I'm hitting 80. And the size of the population is telling me it's going to be predicted to be 8.4 million. So that allows you to make the prediction, which are going to be part of the questions. So the other thing that you're reading on the graph, you read this A, which is the initial size. And then, of course, you need the rate of change, which is my coefficient K. K. And that is what the project is asking you to do, to respond. So that's kind of like in the whole idea behind it. And then the other thing that you need to respond to is what is impacting? What are some global factors? Could be a disease or something else that we don't know. So look at, for the countries that you're selecting, maybe economic issues. So look at those important global factors that are having a huge effect on the population growth. So that is for the first project. Now, the second project does not require you to do some graphical presentation, uses Desmos. So let me go back to content, and then I'm going to go back to where you're looking at. See, still under project option or module. And then I'm going to click on project B. And this is about, again, selecting 2 different countries, but their selection of the countries is based on some famous landmark. So you're first going to select the famous landmark, then where they belong. So where are they located? And then I'm giving you a variety of landmarks just to help you out with some ideas. So one of them is the Eiffel Tower. If you're selecting the Eiffel Tower, that means countries selected automatically will be France. And then you're going to select this particular country because this is where the landmark is located. And you're going to say in the short oral presentation, one interesting fact about that particular country. And then, of course, when it comes to why you're selecting, because you're interested to see something about the Eiffel Tower. And that's the reason why. I'm just making this, saying this as an example. If you're selecting the Leaning Tower of Pisa, then definitely that's going to be Italy. So then you're going to explain, I selected the Leaning Tower of Pisa, and then I'm very interested to see some measurements related to the Leaning Tower of Pisa. And the country is Italy because this is where
the Leaning Tower Pisa is located. This is the only tower that is leaning against the ground level, so it's not standing perpendicular, so the triangle, it's not going to be a right triangle, so therefore the law of sine, law of cosine must be applied in order to find the measurements. The other thing to help you out, I'm giving you the base, because you're looking for shapes, geometric shapes that are going to be triangles. For some of the landmarks, these are going to be the right triangles, and the base is going to be the side, excuse me, the side that relates to the ground level, that particular length, and then the height, which is either the side of the right triangle, or if the triangle is going to be like an oblique triangle, the height is going to be right in the middle of the triangle, so the height is going to create within the oblique triangle right triangles. And then you have to compute the elements that the project is asking you to compute, either by using what you're using. So now let's go back to the information that is needed. So I'm going to go back to content. Where do you find this information? Of course, I'm going to the course materials, and there are three important sections that you're looking at. If the triangle is a right triangle, then you have these nice properties that are part of section 7.1. So what you're using as part of this section, all information about the right triangle, Pythagorean identity. A plus B plus C is the sum of the measures of all angles equals 180. If you need to find the angles, you have to rely on this. But of course, you have to rely on the definition of trigonometric functions. So if sides are given, definitely using the trigonometric functions to find the missing angles in these cases. Now, if the triangles are oblique, you have to rely on section 7.1 and 7.2. So I'm going to go back to this section 7.1 and 7.2 and then give you the information right there, 7.2, where you're looking at. If I click on section 7.2, this is the famous law of sine. Law of sine provides information about oblique triangles. Oblique triangles are classified as acute triangles where all interior angles are acute, and then or obtuse triangle, one angle is an obtuse angle, an angle between 90 degrees and 180. The other two interior angles are acute angles. And this is what we call the law of sine. And then finally, if you go back to the same chapter, chapter 7, section 7.3 is sometimes extremely important because it has the law of cosine. There's a specific scenario where the law of cosine applies, and that's the scenario where you have zero information about the angles. Now, if you pay attention, this is called formulas of the law of cosine. This is all about finding the angles when you have only information for the three sides of the triangle. So how you use them, again, select the landmark that you are interested. You're going to say some interesting facts about the landmark. Based on the selection of the famous landmark, you automatically has selected the country where the landmark is located. And then you're going to see some of the measurements are given, but you're going to search and then find some other measurements that you need. And then you're going to do some computation to find possibly angles, missing sides of those landmarks. The other thing that is part of the version B of the project, you are asked to provide a sketch manually done, not an image that you rely on from the Google Images or any other source, just a sketch of the landmark that has to be provided and then attached to all the information that you're turning in as your package, because this is going to be more likely a package that you're turning in. So these are all my comments for the project. Now I'm going to go back to the course material and then stop sharing all this and then refer to the final part of this video recording, and that is notes for our section 9.3. These are notes that are already typed in. So you see section 9.3, partial fraction decomposition. I always start off with an explanation why we need partial fraction decomposition, and then I give you a step process to decompose a fraction. This is a process that I want you to rely on in order to go through the decomposition of the fractions. And then I'll show you two specific examples. One of them comes directly from the final exam study guide. And that's the one that I'm going to encourage every one of you to rely on and study more than once, okay? Now, where the idea of the partial fraction decomposition comes from. We're so used to have a fraction such as x plus y over 3, where you notice I have two terms, x and y, on the top, connected together by plus, and then a common denominator 3. If that's the case, we're allowed to split up that single fraction into other fractions, where numerator of one of them is x and denominator is 3, and then the numerator of the other is y and denominator is 3. So you can write this as x over 3 plus y over 3. And this is true. So both sides of this are equal. So that's a mathematical identity. It's a true statement, which means you're allowed to split the terms of the numerator, that's the key, as long as you keep the denominator the same. Now, what is not true, the other statement that is next to it. Notice now that the 3 goes on the top, and then the x plus y, so the sum of the two terms belongs to the denominator. You cannot write this as 3 over x plus 3 over y. So the split of the terms of the denominator is a process that you're not allowed to do. You can separate the terms of the numerator as long as the denominator stays the same. That's the statement. So this expression is a false expression. But this brings up the idea of, is there any way possible that somehow whatever we do for the numerator, we can apply to the denominator? And this is where the idea of decomposing comes from. So when this was discovered for the first time, they rely on the two examples that I showed you to create this famous idea that something has to be done somehow to split the denominator. You cannot just randomly split it the way I did it, x plus y. Notice they're connected by a plus, but there's an operation that allows you to do that, and that's multiplication. So as long as you are going to create that multiplication in the denominator, then you're setting up yourself to decompose the fractions the way we normally do for the numerator. So we do have a process that is known as a partial fraction decomposition. And then these are some famous steps that we use to decompose fractions. So remember, the key element is creating a product in the denominator. And the product or the multiplication can be only created by factoring out the denominator. And that's a key element in the process of decomposing the fraction. So we always start off by factoring out the denominator completely. Once you factor out, you are going to identify the factors of the denominator. And there are several cases, possible cases. When we factor out, we can have distinct linear factors. So your expression that you have in the denominator is factored out, and you're creating factors of the form ax plus b. Now, the reason why we call them linear, because the variable has an exponent, variable x, by the way. A and b are going to be replaced by numbers. Variable x is a variable with an exponent 1. So this is a first degree polynomial. That's why we call it a linear. And you are going to have maybe not only one, but multiple factors of this form, and they're all going to be different, not the same. That's why we use the word distinct, to show that they're all different. They're all first degree polynomials, they're all different. And by the way, for this level of calculus, pre-calculus, we rely on this particular type of factor. So when we factor out the denominator, the expectations are you are going to see linear factors that are not going to be the same. Now, there is one that is deeply studied in Calculus 2. You're factoring out, and then you still have linear factors, but they are repeating themselves. So let's say you're simplifying, and then I can add an example next to it to give you an idea what I'm referring to. Let's say I have a quadratic function given as, and that's going to allow you to better understand this, given in the form of x squared plus 7x plus 10, okay? Now, if I decompose this or factor it out, I'm going to have, using the famous AC method, I'm going to have x plus 5 multiplied by x plus 2. And let me put square brackets so we can see the distinction. Now, let's say the denominator is x squared plus 7x plus 10, right? When I factor out, I get x plus 5x plus 2. That's what I'm calling a linear factor, a factor of the form ax plus b, where a is 1 in each of those cases, and then b in one of them is 5, and then the other one cannot be b, it's going to be another c, right? Which is 2. These are distinct linear factors, right? Now, what are the ones that we call a repeating linear factors? So let me copy and paste this, and then I'll make adjustments so everyone can understand why we call them the repeating factors. Now this 7x, I'm going to replace it with a 8. The 10, I'm going to replace it with a 16. And now you realize then when I defoil this, I'm going to get two linear factors, but they're both equally the same. X plus 4, x plus 4. So these are linear, but they're repeated. So you see x plus 4 twice. That's what I'm referring to with ax plus b to the power n. Now, when you have quadratic, and then we're going to see a case of quadratic, you're factoring out the denominator, and somehow one of them is going to be of degree 2. That's quadratic. And you might have more than one of them. And then the same as a linear, you may have two quadratic, but they're repeating themselves, okay? We're not going to get deeply into complicated cases, but will be two examples enough to allow you to understand this process. So after you factor out the denominator, you are going to identify what type of factors you are working with. That's going to determine your next step. Why? Let's see what the next step is. You're going to count the number of factors present in the denominator. So if I factor out, let's say, x squared plus 7x plus 10, I get two factors. So that is going to allow us to set up the fraction decomposition. So if I have two factors, that means I need two fractions. So set up fraction decomposition is based on the number of factors in the denominator. So if I have two factors, then two fractions. The type of factors will determine the numerators of each fraction decomposition. So if I have denominators that are going to be linear denominators, automatically the numerators are going to be constant because the degree of the numerator must be one less than the degree of the denominator. And then I'll repeat this once we get to the example to explain this process. So if the denominator is a distinct or a repeating linear factor, then the numerator is going to be constant. So we call them type A, B, C, D, and so forth. But if the denominator is a distinct or a repeating quadratic, then numerator must be linear. It's going to be of the form ax plus b, cx plus d, and so forth. Why? Because the polynomial expression in the numerator must have a degree 1 less than the degree of the denominator. So if I say the denominator is linear, that degree is 1. So automatically the numerator must have a degree 0. The only term that has a degree 0, which is x to the power 0, x to the power 0 is 1. The only term is the constant term. Constant term has no variable because the variable is of the form x to the power 0, which is substituted by 1. So now let's try to see the steps in this example. This is a final exam review example. So pay attention to the final exam review. And that's the question. So we have this 3 over x squared minus 5x plus 6. So you notice that you have three terms in the denominator connected by a minus and a plus. You cannot split it up the way I did this x plus y. So you cannot put x and then put y on two separate denominators and simply connect the fraction by a plus. That's a false statement, okay? Now, in order to split, you have to use the partial fraction decomposition. So what is step 1? Your step 1 in the process is going to be factor out the denominator completely. And that's what I'm going to do. So I'm going to take the denominator x squared minus 5x plus 6. And I'm going to factor out completely. So using the AC method, I get x minus 2, x minus 3. Now, I notice in the denominator, there are two factors. Both are not the same. One is x minus 2, the other one is x minus 3. That's why I call them distinct linear vectors. Distinct means they're different. Linear means x is of power 1, okay? So there are two distinct linear vectors in the denominator. Therefore, the two fractions are going to require constant at the top. So we have two vectors, we need two fractions. So you see two fractions. And then you see the boxes on the top. So two fractions, one for each vector. One denominator is going to be the vector x minus 2, the other x minus 3. And then I have these two empty boxes on the top. Since the denominators are of degree 1, because x is to the power 1, you don't see the degree, then the numerators are going to be constants. I do not know what the numerators are. So one of them I call constant A, and the other one automatically is going to be B because they're not the same. This is what is called the setup of your partial decomposition. So now what you did is you created a partial decomposition. That's the partial decomposition. So this is the setup of the partial decomposition. This is called partial decomposition. And I'm going to highlight this yellow. So that's what you're looking for when you decompose. Is this completed? No, it's not. Your goal will be completed, fully completed when you find A and B. And that's what I need. Now I need to find a way to find A and B. So now the next step in the process is going to show you how to find A and B. So to find A and B, we're going to use the idea of the least common denominator. Pay attention to the left-hand side. You have a denominator x minus 2 times x minus 3, which I call the least common denominator. Is it possible I can create the least common denominator on the right-hand side so I can make all the denominators equally the same? The way we do it, if we multiply the first fraction by what the least common denominator is going to be. So the least common denominator is x minus 2, x minus 3. So multiply by the least common denominator each side. And that's what I did. That's why you see all in red these denominators. If you multiply by the least common denominator both sides, then the denominator is going to disappear. On the left-hand side, the only thing left is 3. On the right-hand side, x minus 2 disappears for the first term, the one that is in red. So what remains is a, and then times x minus 3. And then x minus 3 is going to disappear in the second term. So what remains is b times x minus 2. Now, this is my brand new equation after multiplying both sides by the least common denominator and then eliminating anything that they have in common. Now I need to find A and B. So what we do to find A and B? There's a variety of ways of doing it. I showed one with distributing A, distributing B, and setting up or equating terms that are sharing the same coefficients of the terms that are sharing the same variable. That's one idea. The other idea is you make variable x equals to 3. So I'm going to show both. So let me start off with the first one. So keep 3 as it is on the left-hand side, and then multiply or distribute a. So multiply a by x. So this purple color, ax, minus a times 3, which is minus 3a. Do the same thing with b. So plus bx minus 2b. Now the purple color tells you that these are terms of variable x, which on the other side, I don't have it. So that means I can add a term on the left-hand side, place a 0 in front of x, so to create what is missing, and then make it purple. So all the purple terms are purples of the variable x. They all share x. So that means the coefficient of the left must be set equal to the coefficient on the right. So the 0 on the left, 0x, must be set equals to ax plus bx, which makes, if I divide both sides by x, which is going to make, in this case, 0 equals, let me write that down, 0 equals to a plus b. So these are the purple terms. Coefficients are equal. And then we have the yellow terms. We have 3 equals to negative 3a minus 2b. These are terms in yellow that have no variable. We call them constant. So the constant on the left-hand side is set equal to the constant on the right-hand side. Now, what this does allows me to solve a system of equation which is in yellow. You can solve it by substitution. You can solve it by elimination. If I solve by substitution, by elimination, then I can eliminate variable A if I multiply my top equation by 3. Because I notice that I have a negative 3a at the bottom. So I need a positive 3a on the top, so I can cancel them out. So I multiply the top by 3, so multiply by 3, both sides. So what I get is 3a plus 3b equals 0, and then I have a negative 3a minus 2b equals 3, which is my second equation, and then add both equations side by side, and that's going to eliminate a. Because my variable 3a, and let's make this a purple, it did the entire expression. Okay, so let's make this entirely purple. So 3a and then negative 3a cancel each other out. So if that's the case, a will be eliminated, and then this only is going to be a variable b remaining. So what remains after adding up 3b and negative 2b, I get b by itself, which is 3, because 0 plus 3 is 3. And then if you substitute b into the first equation, this is my original equation, a plus b equals 0, a plus 3 equals 0, I get a equals 3. So these are the two coefficients which I can easily substitute into the partial decomposition. Remember this yellow partial decomposition right there? So I need a and b. If I substitute them, then I have successfully decomposed my fraction. So I went from 3 over, so the original one was 3 over, so let's take the original one. This is how I started right there. This is my original expression. This is how I started. This original expression was originally decomposed into 3 over x minus 2, x minus 3. And then from that point on, this is fully now decomposed into negative 3, which is coefficient a over x minus 2, plus 3 over, which is coefficient b over x minus 3. And that's what I call partial fraction decomposition. So another possible way of doing it is by relying on this expression right there. So after you solve it, you eliminate the variable. So let me take all this expression, copy and paste it, and then I'm going to call this method number 2. Some students find this one as the easy, so this is method 1. Let's put a name in there. Method 1 to find a and b. And I'm going to highlight this. Okay, now let's use a different color, because these are colors that are already used. Yeah, there you go. And then now I can copy and paste this again and call it method number 2. It's important to show the second method, and then I'll explain the reason why. So what I'm going to do is I will copy and paste only the first part of this. And then this is sometimes considered a shortcut, and students find this method a better option compared to the one that I showed based on the system of equation. So what this method does, you start in a very similar way you started with the first one. Remember, the the original equation, this is what you're trying to solve. You find the least common denominator. So again, you cannot eliminate this step. This is a similar step for both. And then you multiply psi by the least common denominator, which reflects in all this process when the least common denominator is in red. And the other thing that I can do is I can bold this so everyone can have a clear understanding. Now you notice that some of those factors are what they have in common. So the first one on the left-hand side has x minus 2 in common, right? And then the second one, x minus 3 in common. So this is what will be eliminated. And then on the left-hand side, everything is eliminated, right? The entire denominator. And then only 3 remains. But on the right-hand side, after getting rid of x minus 2 in the first term, there's still a remaining and then x minus 3 remaining. So you multiply a and x minus 3. Second term, you eliminate x minus 3, which is bolded in red. The remainings are going to be b and x minus 2. So what will you do next? You solve by setting x, first x equals to 3, to eliminate a. So let's do that. So what you do is make x equals 3. Now, what's the point of making x equals 3? Let me copy and paste this, and then you will understand what the point is. So if I make x equals 3, right there, this is where x is. I'm going to make it a 3. That's in purple, right? Then you are going to see a now will be multiplied by 0. Because 3 minus 3 is 0. Remember, x will be substituted by 3. So that's the substitution in purple. Yeah, the x, it's substituted in purple, okay? And then b will be multiplied by 3 minus 2, which is 1. So that is 3 equals 8 times 0 is 0 plus 1b. So that's going to be 3 equals 1b. And then you divide, which is 1 times b is b. So that makes b equals 3. And then that's one solution, which I'm going to highlight in yellow, okay? Now we repeat this process. So I'm going to copy, paste again, and then make adjustments. So now I'm going to change color. So solve now by stating secondly, setting x equals to 2. And then I'm setting x equals to 2 to eliminate b. So x becomes 2. And then this is where I'm going to change color now. So I proceeded with purple. Now I'm going to make this green. This will be substituted by 2 in green color. So x will be 2. And then this is again green. X will be substituted by 2. So what is going to make this? It's going to turn b into 0. So that's the substitution. So a will be multiplied by -1 because 2 minus 3 is -1. And b will be multiplied by 0. So notice the changes because the 2 minus 2 is 0. That's going to make b times 0, which is 0. And then, of course, a is going to turn into -1 times a. In the next step, we get rid of 0. So now we have -1 a. And you are going to divide both sides by the number in front of a, which is -1 in this case, to find a by itself. So in the next, that's going to be reflected in the next step. So here's the fraction form. You're dividing by -1. And then -1 times a will be divided by -1. So that means a in green equals to -3. Okay. And then once you get a and b, you go back, and then this is your partial decomposition. You substitute. So this is partial decomposition. So how do I write my partial decomposition? The way we did write the partial decomposition at the end for the previous result, where a is substituted by -3, and then, of course, b is substituted by 3. So you start with 3 over x squared minus 5x plus 6, and then you decompose into -3 over x minus 2 plus 3 over x minus 3, and that's the final answer. Now, the second example, it's a little bit more interesting because it allows you to see a scenario where the factor is still linear, but it is repeating itself. So you start off with a complicated expression, -x squared plus 3x plus 8 over x to the third plus 4x squared plus 4x. And then in order to split up or decompose, you have to rely on factoring the denominator completely. So factoring the idea of, and that's the reason why I'm going over the first part of it, and I'll let you look at the coefficients on your own. The details are presented, and then you should be able to follow through. By the way, this is a typical example that you are going to see. It's what I just showed you. This is how far we go in this level of precalculus. But the reason why I'm showing this second example to explain the word completely, which is so important. When I say factor out completely, you have to really factor out completely, and this explains why. So when I look at this expression in the denominator, I see that all three terms share x. So I start off by factoring out the greatest common factor. That should be the first step in the process. If you see that they share a common factor, you always start off by factoring out the common factor. In this case, x. And then if I do, I take out x, the remainings are going to be from x to the third, I get to x squared. 4x squared becomes 4x, and then 4x becomes a 4. I'm not finished. This is factoring out the denominator, but not completely. Now the focus is to the expression that is inside parentheses. The expression is going to be factored out again. And then as you notice, when you factor out by using AC method, you get x plus 2 times x plus 2. Now, what is interesting in this case, you see no changes in the numerator. The denominator now becomes the product of x, and then, of course, a product of x plus 2, which is a linear factor, but one that is repeating itself. So that's why I write it as x plus 2 to the second. Now, what gets different now when you set up the partial decomposition, you're not forgetting about the factor that is repeating itself twice. So when you set it up, how many factors are all together in the denominator? That's going to give you how many fractions you need. You have x, one factor, you have x plus 2, two of them, and then you have x plus 2 again, three of them. So you need 3 fractions to set up the partial fraction decomposition. Now, how do I set up? I start with first fraction x, denominator x, the second one x plus 2. Now notice the third one. You have to reflect that x plus 2 is repeating itself. So then you have to do x plus 2 multiplied by x plus 2. So that's x plus 2 to the second power. So these are the 3 fractions, and that is different when you have a repeated linear factors. So the last one is going to reflect how many times the linear factor is repeating itself. But despite the fact that the third one is repeating itself, when you set up the numerators, these are going to be set up based on what the denominators are. They're all linear factors. So the denominators are going to be A, B, and C in this case, because you have 3 of them. So notice that you have A, B, and C. Now, I added another example. If I have an x minus 1 that is repeating itself 4 times, then you're going to write x minus 1 squared, x minus 1 to the third, and then x minus 1 to the fourth. So you increase that increase the number of them repeating in that particular order. So first one is going to be x minus 1 by itself. Then second one is going to have 2 of them. The third one is going to have 3 of them. And the last one is going to have all 4 of them. And then, of course, the tops are going to be A, B, C, D, because no matter how many times the linear factors are repeating themselves, they continue to remain linear factors. So the numerators are going to be always constant. And this is where I'm going to stop the presentation. Just this is an additional comment on the partial decomposition. You're deeply getting into this when you get into Calculus 2. But your main focus will be on the first example when I gave you 2 different methods to get the coefficients and then went through the entire process of decomposing the fraction. Okay, so good luck reading and then studying. We're not going to go back to the fraction decomposition in class. The focus will be tomorrow on conic sections and then getting into sequences and then 2 special cases of sequences. So this is where I'm going to stop sharing and then stop the recording. I will post this video in Brightspace and then I will encourage all of you to watch the video today and be prepared tomorrow. Okay, thank you for watching.